Hi there. I am making this recording since we cannot have lecture on Thursday, so this way we won't get behind. Okay, today we are mainly going to talk about Naïve Bayes. And we're going to be talking about the first supplementary reading from the Think Bayes book. So hopefully you have read that. You could find that on Canvas, and that was mentioned in the syllabus. So I'm going to start by talking about probabilities in very simple terms, and then we will move into the Naïve Bayes algorithm itself. So within a probabilistic system, there's a notion of an event, like a tossing of a coin. That would be one example. And there are a certain number of things for any event that can happen. We call that possible outcomes of an event. So for a coin toss, it would be that you get heads or tails. In the case of a coin, it's 50-50 if it's a fair coin. So the likelihood that you get heads on a random toss is 50%. Probabilistic systems are nice because they give us a way of proving that we can be correct in how we are doing certain operations. In particular, one of the things that is really important in machine learning in a probabilistic system is that we can combine evidence. So you can combine predictions that are independent of one another by multiplying. So if, for example, if you wanted to compute the probability that you would get heads twice in a row, it's going to be 0.25. Okay, so what does it mean for two events to be independent? We talked about this briefly on Tuesday. And the idea is that if one event happening is not at all correlated with another event happening, they're independent. Otherwise, they are dependent, but they may be conditionally independent given some other condition. And so, for example, it might be the case that we talked about the example of American cuisine. Foods being creamy and foods being sweet are correlated with one another. But the main reason why they're correlated with one another is because desserts have both a tendency to be sweet and a tendency to be creamy. But if you condition on a food being a dessert, now all of a sudden sweet and creamy are not dependent on one another anymore. Because the only reason why they were related to each other was because of the fact that desserts are frequently creamy and they're also frequently sweet. So then, since being a dessert makes both of these more likely, then if you don't consider dessertness, then you see a correlation between these two things. But if you know it's a dessert, then you've already accounted for the extent to which you see sweetness and creaminess. And so beyond that, they are not correlated with one another, and that's what it means that sweet and creamy are conditionally independent given dessert. Okay, so now let's think of a slightly more complicated case. If you're rolling a pair of dice, what is the probability that you'll get a 4 and a 5? Notice that I didn't specify an order here. We have 6 possible outcomes on each die roll. So that means there are 36 things that can happen. 2 of them meet our conditions, and so the probability is 1/18. And I just said how I figured it out. You might want to just pause and think about whether that made sense to you. You can figure it out by thinking about how many ways can each one of the dice land, and how many of these ways that the dice can both land satisfy our constraints. And then we want to divide the ways that we can satisfy the constraints by the number of things that can happen, and that gives us 1/18. Now, if there's an additional constraint that the first die has to be a 5 and the second die has to be a 4, now there's only one way that we can meet the constraints, and it will be 1/36. Or what if you already know, though, that the first die landed on 5? Now there's actually only 6 things that can happen, and one of them satisfies our condition, and so the probability is 1/6. Now, probabilistic models, there are a few things you need to know about them. One is that we think of them as being generative, and this is because they model the world as it's observed, and we think of the structure as being meant to reflect the process through which the observations that we see in the world are generated. Weight-based models are different. They're discriminative. They model decision-making. They bring out what distinguishes one outcome from another. So they, instead of modeling what we see in the world overall, they model what we should notice about the world, and not where it came from, but just what is it that actually distinguishes one class from another, for example. And when we do weight-based model learning, we optimize for the ability to discriminate. And so those models can learn to notice some things and ignore other things. Since probabilistic models just model what we see in the world, then they have no mechanism through which they can ignore something. They don't learn to ignore anything. And so because everything is considered, if we have lots of things that are part of what's being considered, then it's very likely that if there are lots of irrelevant things that are within the set that are being noticed, that the noise overwhelms the signal. And we don't usually get this happening in weight-based models since we can learn to ignore things. And this is a really important distinction between these two. So people who are more strongly in favor of statistical modeling usually fall back on that statistical models are more elegant and there are things that are provably correct. You can combine probabilities in a principled way, and you can also deal with missing variables in a principled way. We'll see later that that we can just drop our paying attention to variables that are missing from a case where we want to be able to make a prediction after the learning takes place. And you just can't do that with a weight-based model. And so that's an advantage of a statistical modeling framework. We have a principled way of scaling back the set of things that we pay attention to make a prediction when we need to. So weight-based modeling people will say, okay, yeah, those things are true, but you have to make a lot of assumptions when you apply statistical models that in general aren't true. In fact, we're going to see a bunch of cases like that. And what are those assumptions and how are they broken and what are the implications of that? So in practice, those statistical models are kind of more theoretically pleasing than weight-based models, which can be thought of as being ad hoc. In general, they don't work better than weight-based models. In the end, it's actually good to combine these things. As I had said in an earlier lecture, I'm actually really happy that these days there's a lot more to combine these approaches. For example, in variational methods used in the deep learning space, we bring both of these two worlds together. And I think that that's a really promising part of the work that's going on these days. So now let's get into the meat of today's lecture. This is what I really want to make sure we get through because on Tuesday, I'm going to assign assignment 2, and you're going to need to be able to work through Naïve Bayes. So Naïve Bayes is based on the ideas behind Bayes' theorem. In Bayes' theorem, we see the relationship between the probability of A given B and the probability of B given A. Typically, A is our class value. We're trying to predict a class value, and what's given is the evidence that we see. So B is a set of variables, and those are our features. Now, we want to be able to make a prediction based on the probability of A given B, but oftentimes it's not very convenient to directly compute that, and I'm going to talk you through why. And Bayes' theorem is going to enable us not to have to model some things that are often difficult to directly model. So Bayes' theorem says the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. What's often difficult to model is the probability of B. So for example, we have been talking about the play tennis data set. And we have this data set, we have a set of days for which we know whether somebody played tennis or not. But what we don't know is overall what is the probability for each one of those days occurring out of all of the possible days that could occur in the world. In general, we feel less comfortable with the idea that we have modeled, that we have kind of a sort of representative distribution across all of our feature values, then that we have something that we can consider a representative distribution across our class values. And so we don't feel so comfortable being able to be required to directly compute the probability of B. And you would need, it's part of directly computing the probability of A given B. But since the probability of A given B, so you can see here it's actually worse if you think about, what is the probability of A equal to? A given B equal to? It's equal to the probability of B given A times the probability of A divided by the probability of B. What we want to be able to do is remove from this the probability of B. And just focus on the numerator. And we're going to talk through why we can do that. So let's say that A has two possible outcomes, yes or no. If we sum the probability of A given B over all possible A's, we should get 1. So what that means is if B is features of a day and A is either yes, we'll play tennis, and B and A, or no, we won't play tennis, then the probability out of that whole set that we play tennis plus the probability out of that whole set that we don't play tennis should sum to 100%, because we're going to do one or the other. Okay, so, and I've already said, sometimes the probability of B is too hard to estimate directly. But what we can do is estimate the probability of B given A from the data that we have. So we know in our data what are the cases where the outcome was A. And so then we can, from those examples, look at the distribution of B's given that A. And so then we can see, each day, how typical does it seem out of the set that we've seen associated with A. And we can also see the probability of A in that set if we believe that we have a kind of representative distribution of outcomes at least, then we can estimate the probability of A as well. So that means that it's not that hard to do the numerator, to multiply the probability of B given A times the probability of A. But there's a problem here. That's not a probability because we haven't divided it by the probability of B that would turn it into that probability of A given B. But it is proportional to the probability of A given B. And we know that because we can compute probability of B given A times probability of A divided by the probability of B for each one of our A's. And then when we take those values and we sum them, we should get 100%. So what that means is that if we have probability of B given A times the probability of A for the first A, and we have the probability of B given A times the probability of A for the second A, these won't sum to 1, but what we can do is look at the proportionality. So if we add them together, the numerator for A1 and the numerator for A2, then that's the total likelihood that we get. And we know that if we divided each of those by the probability of B, we would get numbers that summed to 100%. And so that means that if we wanted to maintain that proportionality, what we could do instead of dividing by the probability of B is divide by the sum of the numerators. And so we would preserve the proportionality and we would get to numbers that would sum and make up a probability distribution. So to get the probability of A given B from the probability of B given A times the probability of A, what we'll do is compute this numerator for each of those A's, then sum those quantities, and then divide each probability of B given A times the probability of A by that sum, so that we see what is the proportion of the numerator for one of those A's over the sum across those numerators for all of those A's. If we know that removing the numerator gives us something that's proportional to the probability of A given B, then we want to maintain that proportionality when we look at the set of all of those for, across the possible A's. And so, and if we want to know what proportion of that total is the probability of B given A times the probability of A, we're going to divide that numerator by the sum across all of those numerators. Okay, you actually might want to take some time to work through that on paper and make sure that you understand it. That's also in the book, and feel free to post questions to Piazza. So now let's think about the same thing from a different angle. So let's consider that we have two classes, A and B, and these classes, A and B, have balls of certain colors in it. And now we're going to randomly pick a ball and try to predict which bowl did it come out of, and that's going to be related to how we would use evidence of the color of a ball to predict which bowl it came from. Because assigning a ball that we see with a color to a bowl is like assigning a day with some properties to an outcome, which is you play tennis or not. In this particular case, it would be like saying that all of the days when I played tennis are exactly the same as each other, and all of the days when I don't play tennis are exactly the same as each other. This is the easiest possible case. In this particular case, if I see one ball, I know exactly which bowl it came from. And if I pick two balls, I can do the same. And I can combine to figure out which bowls these two balls came from, just as we have discussed about combining across probabilities. Now the situation becomes a little bit more complicated when our bowls are not totally homogeneous. Now if I see a red ball and a blue ball, it's still the case that most likely the red ball came from bowl A and the blue ball came from bowl B, but that's not entirely obvious that it had to be that way. So let's work through the math, and let's start with only one ball. Again, you might wish to pause this every once in a while. You may wish to re-listen to things that I've said. I'm probably talking a little bit faster than I normally would in lecture, and obviously I can't stop and ask for questions, but you can stop anywhere along the way, listen things as many times as you need to, and post questions to Piazza. And hopefully we'll all get through this, and hopefully no more lectures will be canceled. So we're going to start with that first ball. And we're going to first compute what is the probability of any ball in the world, regardless of color, coming from bowl A or bowl B. That's the prior probability on the class value. That's like the probability of A that we talked about before, or probability that you play tennis. And in this case, the bowls are the same size. So we're going to say the probability of bowl A is a half, and the probability of bowl B is a half. Half of the balls in the world are in bowl A, and half of them are in bowl B. We also want to know the probability of the feature that we're talking about, which is color. And so the probability of red in this case is 1/2 also, because half of the balls in the world are red. And the probability that it's blue is a half. Now, if we wanted to compute, because we can see these bowls, we can compute the probability of a color given a bowl. So we know that the probability of red given bowl A is 7/8 and the probability of red given bowl B is 1/8. So now we can compute what is the probability of red given bowl A times the probability of bowl A, and that's going to give us 7/16. So the likelihood that this red ball came from bowl A is 7/16, but that's not necessarily a probability, and we'll see why. Because now we can compute also likelihood that this red ball came from bowl B by the probability of red given bowl B times the probability of bowl B. That gives us 1/16. Now we know these are not probabilities because 7/16 plus 1/16 isn't 1, it's a half. So that means we need to scale these. So we would say that 7/16 plus 1/16 is our total probability mass. We know that our numerators are proportional to probabilities. So what we want to know is 7/16, what proportion of the total probability mass is that? Well, 7/16 divided by 8/16 is 7/8. So that means the probability that A came from bowl A, this ball, the red ball, came from bowl A is 7/8 and not 7/16. We have to scale it. We want the probabilities of the two possible outcomes to sum to 1. And so likewise, the probability that it came from bowl B is 1/8. So now we know the probability for that first ball, but we can do the same for the second ball. And because these are kind of mirror images of each other, we're going to end up with a probability that it came from bowl B being 7/8. So now if we want to say what is the probability, what is the most likely case when we see a red ball and a blue ball, then we have to compute the probability of each possible combination. So there are 4 things that might have happened. Red may have been from A, blue from A, red from A, blue from B, red from B, blue from A, red from B, blue from B. And we can assign probabilities to each of these, and we saw how to do that. Then we can multiply them because the 2 draws, we draw a ball out of the bowl and then put it back. So we never change our bowls. Therefore, the probability distribution of how we would attribute a ball to a bowl doesn't change just because we've already drawn a ball before. So they're independent, which means we can just multiply these probabilities, and you can see the probabilities associated with each of these possible ways that we could have seen a red ball and then a blue ball. And the one that is more likely than any of them is that the red ball came from bowl A and the blue ball from bowl B. But you can see that, there's some probability associated with all of the other combinations. And so while this is the most likely thing to have occurred, it's not 100% certain. So now let's think about how you would use those ideas to train a model. And for using our model, we want to be able to look at some data and make a prediction about whether we should play tennis or not. So we can compute things that are analogous to what is the probability that if you were drawing out of bowl A, you got a red ball. The analogy here would be something like the probability that the outlook is rainy, given that play is yes. How would you actually compute that? What you would do is look for all of the rows that were yes and see what proportion of them have outlook rainy. So first we pick those instances with outcome yes, and then we look at just those ones that are rainy. And you can see that there are 3 that are rainy and yes, and there are 9 that are yes. So a third of the ones that are yes are rainy, yes. yes, rainy, which means that the probability of outlook rainy given play is yes is 1/3. Okay, so then how do we compute the likelihood of playing yes if what we see is that the day is rainy? So what are we going to do? So we know that the probability of A given B, so that would be like the probability of playing tennis, given that you saw that it was rainy, we want to know what that probability is. But what we can find is the probability of rainy given yes, which is 1/3, and we know the probability of yes. It's the total proportion of yeses that we see. So if we multiply those together, that's the likelihood that we saw before when we were talking about balls and bowls. And remember that when we computed it that way, we said it's not a probability yet, but it's proportional to the probability that we want. So first we have the probability of rainy given yes, and you can see here how we compute that. We count the number of times that it's both yes and rainy, which was 3, and divide by the number of times it was yes, which was 9, and that gives us 1/3. And we're going to multiply that by the proportion of times over the whole data set that the outcome was yes. Now, what if we had more than one feature? Now, what we do is we take into consideration that each of our feature values is conditionally independent given our class value. We talked about what that meant. So if we know that we're not playing tennis, the fact that it's sunny isn't related to the fact that it's hot at all. Actually, here it looks like it's the opposite of what you would expect, that sunny and hot are on days when you don't play tennis. Maybe because it's too hot if it's both sunny and hot. It's a small data set. It doesn't have to make sense. But the idea here is this. Those conditional probabilities, like that it's sunny given that we're playing tennis or sunny given that we're not playing tennis, are independent from the conditional probabilities on another variable. So sunny given no is independent of hot given no. That means that outlook and temperature are conditionally independent given the class value. Because of that, if we want to combine evidence, we can multiply. That means that the conditional probabilities for each one of our variables that are predictor variables conditioned on our class value can be multiplied together in our likelihood formula. So that's a key assumption that you'll see in Naïve Bayes, because in fact we will multiply, and in doing so we are showing that we're making that assumption. So here is what the likelihood looks like when we're considering more than one conditional probability. You can see, if you look in the kind of middle of the screen, there it is. Likelihood of yes equals count yes and rainy divided by count yes. That's the conditional probability of rainy given that play tennis is yes. And then we're going to multiply that by the conditional probability of hot given yes, which is the number of times it's yes and hot divided by the number of times it's yes. And so we've combined those two pieces of evidence, the outlook and the temperature, and now we're multiplying finally by the prior probability of yes. That's always the last thing we multiply in our likelihood, and that is the number of times it's yes divided by the total number of instances. Now, when we multiply in more than one conditional probability, with however many that we multiply in, the total likelihood number is getting smaller and smaller and smaller, because every time you multiply by a fraction, you get a number that's smaller. So we're getting farther and farther away from our likelihoods even looking remotely like probabilities, because they're going to be very small, and when we sum them, we're still going to get a very small number. It's not going to be anywhere close to 1. But just like we did in the balls and bowls example, we're going to normalize. We're going to compute the total probability mass by summing across the likelihoods. And we need to do a likelihood computation for every possible outcome of the event. We sum them together, that's our total probability mass, and we can turn each likelihood into a probability by dividing it by the probability mass. So that's called normalizing, and here we see ourselves doing that. So the likelihood that play equals yes, when outlook equals sunny, temperature equals cool, humidity equals high, and windy equals true, you can see how it is that we're multiplying conditional probabilities for each one of those variables that tell us something about the day, and then finally the prior probability of the class, and we get a very, very small number. And if we want to turn that into a probability, we're going to take that very small number. You can see here I've rounded it a bit. I dropped a few digits, but 0.005 is not that different from 0.005291005. I just shortened it a bit. And what is that number I divided by? That is the total probability mass. You won't be able to see where that one came from until you look at the next bullet point, where now I'm doing the likelihood computation where the class value now instead of yes is no, but all of the feature values are the same. You can see that the conditional probabilities and the prior probability have changed because now we're talking about the prior probability of a different class, the no class. And so the conditional probabilities are all conditioned on those instances that weren't conditioned in the first one. So you can see here we get a small number. It's not as small as before. So, and these two numbers, the likelihood of yes and the likelihood of no, they are each proportional to their corresponding probabilities. And so we need to scale so that we get numbers that we can sum together that come out to 100%. And we can do that by, once we've summed them, and the sum across the two likelihoods is 0.019 approximately if we round it. So that means that to get the first probability we want, it's 0.005 divided by 0.019. We get 27.8%. And for the probability of no, we get 72.2%. Now, one thing that's really nice about these probabilistic models, I mentioned it very briefly up front. If you're missing some information, you can simply drop that conditional probability from the set of things that you multiplied together, and you would drop it both for your likelihood computation of yes and for your likelihood computation of no, so that those numbers are still proportional to one another and you can still normalize and you still end up getting probabilities out. So you can see here that I've reduced the number of features that I am computing conditional probabilities for when outlook is not known. I'm just dropping that first conditional probability. Now I'm only multiplying 3 conditional probabilities before the prior probability of the class. And that's okay because I'm going to do the same thing when I do the corresponding likelihood for no. And so then they're still proportional, and so you can still do the normalization the same way, and you end up with probabilities, and it's all good. Now, so far, we have always talked about naive Bayes for nominal values, and we need to be able to do it also when our attributes are numeric. And so now we're going to come back to the idea of fitting a distribution to some numbers. When we have a numeric attribute, then we have a set of numbers that attribute ever took. We can take the set that it ever took when the outcome is yes, and we can have the set that it ever took when the outcome is no. We would fit separate normal distributions to each of those sets and compute the mean and the standard deviation so that we can turn any number into a probability based on which probability band it falls in. So the probability that the value is within one standard deviation of the mean is 68%. The probability that it's within 2 standard deviations of the mean is 95%. So you can see by looking at how far out a value is from the mean in terms of the standard deviation, we can turn that into a probability, and that's where the conditional probabilities come from when we have numeric attributes in a naive Bayes model. Once we've turned each number into a conditional probability, we can apply the naive Bayes algorithm exactly the same way. So here's an example. If we have a feature value that takes on the values you see up here, 83, 70, 68, 64, 69, 75, 75, 72, 81, when play is yes, and then we can compute the mean, which is 73, the standard deviation, which is 6.16. And for no, we have another set, and it has a mean and a standard deviation. Now we can take this formula that you see that's derived from the formula for the naive for the normal distribution that takes the mean and the standard deviation and the number that you see and turns it into a probability. Then you can get that conditional probability. And so let's say that this is temperature now. And you want to say typical temperatures for yes are what you see in the first bullet point. Typical values for no are in the second sub-bullet under the second bullet point. Once you have the means and standard deviations, if you have a temperature value, you can use the formula you see under compute likelihoods to compute a conditional probability for each possible outcome, and then you can take that conditional probability, plug it into our naive Bayes formula, and you get the likelihood for each class value, which you then normalize to get the probabilities. So once you can do this computation of the conditional probability from the number, you do everything the same. So in addition to the assumption that all of our features are conditionally independent given the class value, another important assumption of naive Bayes is that the distribution of values for every numeric attribute is normal over this set of instances related to each class value. So it's not that over the entire data set that feature is normally distributed, but if you divide the data set into piles according to class value, then within each pile, if you look at the set of numbers that one attribute ever takes on, that set of numbers fits a normal distribution. So there's a question, does this hold for text if we're counting number of times we've ever seen a word in a text? Can we compute conditional probabilities on the presence of a word in order to make a prediction? And so let's think of two possible ways that we might represent the value of a feature if the feature is a word in a text. One is to treat it as a binary, that it's true if you ever saw that word at least once and false otherwise. Otherwise, you might do counts. You might count the number of times that a word ever appears. And if you look at the distribution for any given word over typical texts, it's far from normal. It's heavily skewed towards 0, and it's rarely above 1. And any number above 1 happens very, very rarely. So you'll see something that looks more like an exponential, like you see here. So here is a data set where every feature is a word, and it's represented in terms of counts. And if you look at how it's related to each class value, you'll see that you have this kind of exponential curve in the histogram. Now, simple naive Bayes makes the assumptions we've talked about already, but other versions of naive Bayes don't necessarily make these assumptions. You can always swap out distributions and then compute your conditional probabilities differently. We're not in any way stuck with the assumptions behind plain and simple naive Bayes. And so if we picked a formulation that didn't make the assumptions that in this case are not valid, you could imagine the model will fit better and do better. And here's a simple experiment that shows that. So we have two versions of naive Bayes. The typical version of naive Bayes that makes that assumption that our numeric attributes are normally distributed within class values, and multinomial naive Bayes that does not make that assumption. And we have two ways of encoding our word features, one as binary and one as counts. And you can see that the one place here in the experiment that does poorly is when we use the plain and simple naive Bayes with a representation that violates the assumption of normality. So if we use count features, then simple naive Bayes is bad. The reason is because since it's not normally distributed, it's exponentially distributed, the standard deviation is going to be much wider than it should be. That means every value looks typical, or many more values look typical than should, which means that those features fail to distinguish between cases that are one class value and another. If we use a representation that doesn't violate the assumption, we don't have that problem, and so we do better. If we use that representation, the count representation, with the formulation that doesn't make the assumption, we also do fine. Or if we neither use that representation nor assume that something that's not true, we also do fine. So the problem happens when we use a formulation that makes an assumption that's strongly violated. And it's not that it crashes. You can still apply naive Bayes in that case. It's just that the conditional probabilities that you compute are not very informative. They're telling you something that's not actually true, that every value seems a lot more typical than it really is. And because of that, those conditional probabilities lose their utility, and then the model doesn't work very well. Now, you can play around with naive Bayes using a simulation I put together for you in Excel, which you can find on Canvas. And this is a really simple simulation. Basically, the idea is it's for a binary prediction task. So you've got true or false are the outcomes. Well, you've got two classes. We'll just call them the minority class and the majority class. And what makes the minority class is that it happens a minority of times, and the majority class happens a majority of times. If you look at the class count column, you see 33 under minority class, 67 under majority class. So 33 is less than 67, and that's why that's the minority class. And then we have our features, raw x, raw y, and raw z. And what we're showing here is out of the number of instances that we say are of a class value, how many of them have a 1 for that feature value. So when you see the 33 under raw x in the min class row, that means that out of the 33 min class instances, 33 of them have a 1 for raw x, 15 of them have a 1 for raw y, and 1 of them has a 1 for raw z. From this, you can also figure out how many of them have 0 for those features, because if it doesn't have a 1, it has a 0. And you interpret the majority class row the same way. These yellow numbers are numbers in the simulation that you can change. The numbers that are not yellow are computed from those. So what you see in the prior class column is the probability for each one of these class values, the prior probability. So it's like the probability that you play tennis or the probability that you don't play tennis. Now we have here something called smoothing, and I haven't described smoothing to you yet. I will describe it to you in just a few minutes. When you smooth, what you do is add 1 to every count for your pairing between a feature value and a class value. So whereas you had 33, 15, and 1 for your raw counts on x, y, and z for the minority class, when you smooth, you add 1. And this spreadsheet will do that for you. What you can change or not is the one that's in the smoothing column that tells the simulation that you want to use smoothing or not. If it's a 1, it uses smoothing. If it's 0, it doesn't use smoothing. And so then the count X, count Y, and count Z is the number that it's going to use in its computation for the likelihoods and ultimately probabilities. So if you have smoothing 0, it takes the original values under raw X, raw Y, and raw Z. If smoothing is on, it takes the ones under smoothed. We're going to talk about smoothing, what it means, why we do it, just after this, but I just want you to see you can turn that on or off. And then you get to decide instance 1 has an X val, a Y val, and a Z val. That's the final place where you have yellows. You can fill that in with the feature values of an instance that you want to classify. Then it's going to compute the conditional probability of each feature value as you see it, given the majority class, so that it computes the likelihood of the majority class. And it's going to do the same for the minority class. Then it's going to look at which one of those is bigger. Actually, the minority class conditional probabilities you see just under the majority class ones. And then you see the prediction, whether it picked the minority class or the majority class. What I don't show here is the turning these likelihoods into probabilities. You could actually add that to the spreadsheet yourself if you were interested. But what I wanted you to be able to do is play around with what is the proportion of minority class to majority class, how many for each class have each of our features, so you can have some of the features be really predictive and others not very predictive. You can turn smoothing on and off. You can try different instances and then see what the prediction would be, just to give you kind of more of a hands-on feel of Naïve Bayes. Now you'll see that in assignment 2, which will go out on Tuesday, that you're going to either compute a Naïve Bayes model by hand or you're going to write Python code. What I will not allow you to do is use a spreadsheet because I've given you a spreadsheet that has Naïve Bayes in it. So that's why I want to see you do it either on paper or in Python, but not in Excel. So let's talk about smoothing and then we'll close this session for the day. You have to think now. In theory, you can compute a Naïve Bayes model from any number of instances, and you can have any number of features, and those features can have any number of values. But you should consider how many different probabilities are you trying to estimate, and how many instances are giving you any evidence that would help you to get a good estimate on those probabilities. And oftentimes, when you get down to that level of thinking about what's going on, you start to see that you don't have as much data as you'd like to have. And some of your probabilities are based on very few observations. And the downside really is that sometimes there are combinations of feature values and class values that you've never seen, so the count is going to be 0. And the more features you have, the more likely it is for any given instance that one of those 0 counts is there. And what we want to look at here is what is the problem with that. So we're going to start with a very, very small data set. This is our ice cream data set. We're trying to compute how much you liked a dessert based on what kind of cake and what kind of ice cream it was. Okay, so let's say we wanted to do this for strawberry ice cream and chocolate cake. So what we would do is compute our two conditional probabilities there's going to be 2 for each one of our class values because we've got a value for the ice cream and a value for the cake. And you can see, and you can just work through it on your own. So for strawberry given yum, it's 25% because a quarter of the cases that were yum had strawberry ice cream. Chocolate cake given yum is 75% because 75% of the yum cases had chocolate cake. And 66% of the data points were of the yum class, so we can compute the conditional probability by multiplying our two conditional probabilities by that prior probability per class. And we can do the same thing for each one of our class values. But we never saw strawberry ice cream with good. So that count is 0. So that conditional probability is 0. Therefore, when we multiply out that likelihood, we get 0. Similarly for okay, there we never saw strawberry with okay, and we never saw chocolate cake with okay. Both of these come out to 0. So again, our likelihood is 0. So we're going to predict that our strawberry ice cream and chocolate cake is yum. But we don't feel very good about the fact that 2 of our conditional probabilities turned out to be 0, because at least in the case with good, chocolate cake being good, there was one very strong predictor. The chocolate cake given good has a conditional probability of 1. So it doesn't feel very good that that likelihood came out to 0, but that's the math. It leads us to do that. So we feel like if there are zeros, we're just totally losing part of our reasoning here. And if it had been not 0, but some very small number, then we wouldn't have had that problem. So smoothing is about getting rid of these 0 conditional probabilities so that we don't zero out some likelihoods just because of 1 0, because there might be some very good predictors that we'll just be essentially throwing away. So in order to do that, here's a case that's even worse, actually. In this particular case, every single one of our likelihoods has a 0 in it, and so then we end up not being able to make any prediction at all. That's for vanilla cake and vanilla ice cream together. Okay, so what's the solution here? The solution is what we call smoothing. So we have the counts of how many times we've observed every feature value with every class value. If we make a matrix of all of those counts, there are some zeros in our matrix. If we just add 1 to every single one of those counts, then we have no zeros. And if we use those, what we called smooth counts, instead of the raw counts, then we won't have 0 conditional probabilities, and we won't have the problem that we saw. If you look at these two matrices up above, these are the smoothed matrices. You can see, for example, in the chocolate row, we see 2 on yum. Oh, that's for ice cream, by the way. 2 on yum, 1 on good, 1 okay. Ice cream is the first feature, and we had seen 1 chocolate ice cream with yum and 0 for good and 0 for okay, but when we smooth it, we add 1 to each of those, so we get 2, 1, 1. And these whole tables are all filled out just like that. And then once we have those tables, we can compute our conditional probabilities from this smooth table instead. And so then we end up, and you can see here I've left the prior probabilities unsmoothed. You could actually do it either way. It usually doesn't make that much of a difference. You don't ever really need to smooth your prior probabilities because in general they won't be 0. There will be a case, a weird case of a new feature value being added in on the homework assignment, but there won't be a new class value, so you won't have to deal with that. Normally, you wouldn't add a class value to your model that you've never observed because you have no basis for ever predicting it, and so smoothing doesn't seem like it really extends to that case anyway. So, but some people smooth their prior probabilities by adding 1 to every count on class values, and you could do that if you wanted to. It's not really wrong, but when you smooth, you should note that what happens is things that are very likely look less likely than they did before after you smooth. Things that looked very unlikely look a little bit more likely after you smooth. So what you do is you kind of water down the distinction between things that look very likely and things that look very unlikely when you smooth. And so you're doing that if you smooth your prior probabilities, and you don't really need to, so you might be shooting yourself in the foot. Still, if you do that, I'm not going to count it as wrong. I'm just saying that because lots of students have asked me about that in previous semesters. Here what you see is that the conditional probabilities are based on the smooth counts, and therefore for vanilla cake and vanilla ice cream, we don't zero out any of our any of our likelihoods, and so we do have a basis for making our decision, and finally we decide that this counts as okay. Okay, So we've gotten all the way through Naïve Bayes. We'll talk about weight-based models next week. You have all the information that you're going to need for assignment 2, which I will assign on Tuesday. So hopefully you will listen to this lecture first, considering that classes are canceled, but that doesn't mean that that you guys are not still students. So hopefully you're keeping up, and we'll move on to weight-based models on Tuesday, and you'll have a week from Tuesday to get that second assignment done, which is about Naïve Bayes. So post your questions to Piazza, and I will see you next week.